Hello learners, welcome to the next session of quantum neural network. So in this session we are going to discuss about what is quantum neural network. So as per the definition, quantum neural network combines quantum computing principles with the neural network architecture to process the sequential data. So we have a key features are there. So in the first feature we can easily enhance the capacity for temporal patterns, and we can easily align with quantum superposition and entanglement. So we can have many applications are there. So time series prediction, natural language processing, and quantum sequence modeling. So why QRNN? We have many challenges in classical RNN: vanishing and exploiting gradients. So in the case of vanishing gradient, the model to ignore long-term dependencies. In the exploiting gradient, is happen with the help of large weight updates leading to instability. So we can have a next challenges is there: computational inefficiency for large data set and high energy consumption. We can have many advantages where we can easily cover the classical RNN with the help of quantum QRNN. So in the quantum QRNN, efficient use of high dimensional Hilbert space also to be used, faster convergence of certain problems are to be applied, and scalable temporal data handling to be applied with the help of QRNN. So we may have a different key components are there. The quantum memory states. In quantum memory states, qubits store and update sequential information, and quantum gates are also to be applied to perform recurrent transformation with the help of C0 and HADMOD. Next is the parameterization using the trainable gates for optimization. The next is measurement. Outputs are obtained through quantum state measurements. Hybrid layers are also to be applied here. So combine quantum and classical operations for flexibility. So next is quarking flow. The first one is data encoding. Sequential data is encoded into quantum states. The next is recurrent quantum layer. Update the state using quantum circuits. Applied parameterized gates to simulate recurrence. The third one is measurement. Extracts outputs from qubits. The fourth one is optimization. Classical algorithms minimize the quantum loss function. And the fifth one is prediction. We can easily predict the output with the help of sequential predictions. Here we can go for a small matrix. We have a 2 into 2 matrix for quantum data encoding. To encode a 2 into 2 matrix in quantum state, we consider each row as a basic state. Row 1, 1, comma 0 is encoded as 0 get, and row 2, 0, comma 1 is encoded as 1 kit. The combined state is represented as a kit, which is equal to um, 0 kit plus 1 kit. So this is a normalized form, so which is equal to 1 by root 2 0 kit plus 1 kit. So the parameterized quantum circuit is to be applied here. The QNN applies parameterized gates to input quantum state. A simple circuit includes rotational gate Ry of theta, rotates the qubits about the y-axis. Ry of theta, which is equal to cos theta by 2 minus sin theta by 2, sin theta by 2, cos theta by 2. Measurements, we can have the simple measurements within the each state. The next is applying the circuit. Each input state 0 kit, we can represent it as input state 0 kit and input state 1 kit. So Ry of theta 0 kit, which is equal to cos theta by 2 sin theta by 2. Similarly, Ry of theta 1 kit, which is equal to minus sin theta by 2 and cos theta by 2. The output layer also to be applied here, and A out kit, which is equal to Ry of theta dot 1 by root 2 matrix of 1 1. So substituting Ry of theta, we can also get like this. Performing the matrix multiplication, finally we will get as A out kit, which is equal to 1 by root 2 cos theta by 2 minus sin theta by 2 and sin theta by 2 plus cos theta by 2. So we can have the different kind of measurements are also there. The probability of measuring 0 kit is obtained by squaring the amplitude of each component. Probability of 0 kit, we can also get like this: cos theta by 2 minus sin theta by 2 by root 2 of whole square, and probability of 1 kit, which is equal to sin theta by 2 plus cos theta by 2 by root 2 the whole square. So as per the result, we will get like this: A out get, which is equal to 1 by root 2 in matrix 0 root 2, which is equal to 1 get. So this shows how the QNN transforms the input data based on the theta values. So here we may have a different advantages are there: temporal data efficiency and high dimensional representation, reduced training time, energy efficiency. In the temporal data efficiency, we can easily align with quantum entanglement for a sequential pattern. For the high dimensional representation, we can use Hilbert space for state transitions, and reduced training time, faster optimization for specific data to be applied, specific data sets are to be applied. Energy efficiency, we can also use lower energy use of large classical RNN. So as per the challenges what we faced in other algorithms, here also we can have quantum hardware limitation is there due to the noise and limited qubits, data encoding and overhead for sequential data into the quantum state, scalability handling large sequence and current quantum devices, and hybrid complexity for integration of classical and quantum layers. Thank you, learners. With that information, we will close neural network and RNN with the help of quantum computing. So we will see in the next session.